In Chapter 9, we're going to talk about discrete math. There's two basic types of math. There's continuous and there's discrete. Everything you've dealt with in Algebra 1 and so far in pre-calc geometry, that's continuous math. Okay, we have a value of real numbers within an interval, okay, that help us relate to calculus concepts. All of those values were continuous. What we're going to talk about in this chapter is discrete math, which is basically you can think of as your natural or counting numbers. Okay, so when we're talking about discrete math, we're dealing with probability and statistics, permutations, combinations, the binomial theorem. Okay, so we're going to deal a lot more with probability and statistics in discrete math. So in this first lesson, we're going to talk about the basic combinatorics, okay, dealing with permutations and combinations. In this lesson, we're going to focus on the multiplication principle of counting, also known as the fundamental counting principle. We're going to deal with permutations and combinations. So those are the three things we're going to focus on. We've already discussed briefly discrete versus continuous math. The multiplication principle of counting, here's our general rule or understanding for this principle. If a procedure P has a sequence of stages, S sub 1, S sub 2, all the way to S sub n, and each of those stages can occur in R sub 1 ways, and so on all the way to R sub n ways. Then to find the number of ways that the procedure P can occur, to find all of the different outcomes, we simply have to multiply all of the outcomes for each stage together. So we would take R sub 1 times R sub 2 all the way to multiplying by R sub n. To put the fundamental counting principle into perspective, suppose I have 5 shirts, 3 pants, 4 shoes. Okay, so each of those, the shirts, pants, and shoes, those would be the stages. The numbers representing each of those, the 5 shirts, the 3 pants, the 4 shoes, those would be the R sub 1, R sub 2, R sub 3 different outcomes for each of those stages. So basically what this principle is saying is, if I want to find the total number of outfits that I could create with 5 shirts, 3 pants, and 4 shoes, all I'm going to do is multiply all of these outcomes together. So I'm going to take 5 times 3 times 4 to get 60. So the fundamental counting principle says if we multiply 5 by 3 by 4, all of these different options, multiply them together, I would have 60 different outfits that I could create. Here's another example using the multiplication principle. If a license plate has 4 letters followed by 3 numerical digits, we want to find the number of different license plates that could be formed if there is no restriction on the letters or digits that can be used. Okay, so if there's 4 letters and then 3 digits, there's 7 total characters that we're going to have on the license plate. So if you think about the alphabet, if we're picking for that first character 1 letter from the alphabet, there's 26 different options we could have. So we're going to take our total outcome, possible outcome 26. Now for the second character, if we're picking another letter, there is still 26 different possibilities, 26 letters in the alphabet, so we're going to multiply by 26. For the third character, we're picking another letter, so we're going to multiply by 26. And multiply by 26 again for the fourth character, that is going to be a letter. Now, the first 4 letters are going to be followed by 3 numerical digits. Okay, so for each digit, if we think about 0 through 9, there's 10 different possibilities. So we're going to multiply by 10 for each of those characters. So we have, for the first 4, each one of those, there's 26 different possibilities. For the last 3, there's 10 different possibilities. So the multiplication principle says we multiply these outcomes together. And if we do that, we get 456,976,000. So if we have a license plate where the first 4 characters are going to be letters and the last 3 are going to be digits, there's 456,976,000 possible license plates that could be created. Now we're going to talk about permutations of a set. If we're trying to find the basic permutation of a set, we have to take n factorial. Okay, that's what the n exclamation point means. Exclamation point stands for factorial. For instance, if we had 3 factorial, that means we're taking 3 times 2 times 1. Okay, so we start with the number we have in our factorial, and we multiply in descending order by increments decreasing by 1 each time. So we take 3 times 2 times 1. If it was 5 factorial, we would take 5 times 4 times 3 times 2 times 1. So for an example using the idea of this basic permutation, say we take the letters in the word dragon. Okay, each of these letters is individual, meaning none of them is repeated. Suppose we want to take these 6 letters and find out how many different ways we could arrange the letters. Okay, they don't have to make up a word that you would find in the dictionary. We just want to determine how many different ways could we arrange the letters from the word dragon. Okay, so we look, there's 6 total letters. So from this principle, or this idea, there are 6 factorial different ways to arrange these letters. Meaning, we're going to take 6 times 5 times 4 times 3 times 2 times 1. Okay, so 6 times 5, we get 30. 30 times 4, we get 120. 120 times 3, we get 360. 360 times 2, there are 720 different ways to arrange the letters in the word dragon. Next, we're going to discuss distinguishable permutations. Okay, this will occur when things are repeated. Okay, meaning you can't distinguish one object from another. They seem to be identical to each other. Okay, so now we have another expression we can use to calculate distinguishable permutations. Okay, so we're going to take n factorial divided by n sub 1 factorial, n sub 2 factorial. The n sub 1 factorial stands for how many repeated or identical objects there are. Okay, so if we look at an example similar to the last problem, suppose we have the word bumblebee. Okay, we want to determine how many different ways could we arrange the letters in the word bumblebee. So what we're going to use is the basic idea of a permutation. We got to count how many total letters there are, which is 9. So we're going to take 9 factorial, but then we need to divide that value by any number of objects that are repeated. So we can see there are 1, 2, 3 B's. We can't distinguish one B from another one. They are identical to each other. So we need to divide by 3 factorial. Also, we're going to look, there's 1, 2, 3 E's. We can't distinguish one E from another. They're identical to each other. So we have to divide by another 3 factorial. So now we can use our calculators to go through these calculations dealing with larger factorials. If we type in 9, click the math button, go over to probability, number 4 is the factorial. So we're taking 9 factorial divided by, make sure you use parentheses, 3 factorial times 3 factorial. So we type that in, calculate, we get 10,080. So there would be 10,080 different ways to rearrange the letters in the word bumblebee when taking into account not being able to distinguish the 3 B's from one another or the 3 E's from one another. Now we're going to talk about the permutation counting formula. This is the one that's probably used most often. So if we have n total objects and we're choosing or taking r objects out of there, we have this formula we can use. NPR is equal to n factorial divided by n minus r factorial. For a basic example, suppose we had 6 total objects and we're taking 4 objects out of there. Using this formula, we could rewrite this as 6 factorial over 6 minus 4 factorial. 6 factorial, we can rewrite that as 6 times 5 times 4 times 3 times 2 factorial. The reason I did that is because the bottom simplifies to 2 factorial. So anything divided by itself, those eliminate. So we're left with 6 times 5, which is 30, 30 times 4, which is 120, 120 times 3, we would get 360. The counterpart to a permutation is a combination, which if you look at the formula, if we have n total objects and we're choosing r, the formula is going to be very similar. Okay, the only difference is in the denominator we have an extra r factorial that we need to account for. So for example, if we use again 6 total objects and we're choosing 4, if we take into account that this is a combination rather than a permutation, using the formula we have 6 factorial over r, which is 4, so we have 4 factorial. 6 minus 4 factorial would be 2 factorial. And you can type that into a calculator like we did before and simplify, and you would get 15. So what distinguishes a permutation from a combination? The main difference is that order does not matter in combinations. Okay, if you think about the formula, the only difference between the two in the formula is for a combination, there's an extra r factorial in the denominator. That's accounting for all of those repeated ideas. Okay, the order does not matter in a combination. That is the main difference between the two. Determine whether the situation is best described with permutations or combinations. Okay, for part A, a president, vice president, secretary, and treasurer are chosen from a 20-member club. Okay, the way these individuals, the president, vice president, secretary, and treasurer, the way they'll be selected, that matters. Okay, so this would be a permutation. For part B, a gambler receives 5 cards out of a deck of 52 cards. Okay, say this was for a game of poker. This would be a combination. If you're thinking about a poker hand, it does not matter the order in which the person receives those 5 cards. All that matters is the 5 cards they end up with. That's why that would be a combination. Part C, a teacher makes a seating chart for 16 students in a classroom with 20 desks. Okay. This would be a permutation. The way the students are arranged in the desk does matter. Suppose 10 students try out for 5 roles in a school play. And how many ways could the roles be assigned? Okay. Assuming that these 5 roles are distinguished, okay, each role is different, the order in which they're assigned then does matter. So this is going to be a permutation. So we have 10 students trying out, there's 10 total objects. This is a permutation. There are 5 roles, there's 5 objects being taken out. So this is how we could set up the permutation. Okay. Now that we understand what the formula is, we can use technology to simplify this. So if we type in our 10 total objects, go math, go to probability, the second one down, our permutation. We have 10 total objects, 5 roles are being assigned, so if we calculate this, there would be 30,240 ways the roles could be assigned. So 30,240 different ways to assign 5 roles out of 10 students trying out. In the Miss America pageant, 51 contestants must be narrowed down to 10 finalists. And how many possible ways can the 10 finalists be selected? In this case, it doesn't matter if you're the first, second, third, or 10th finalist selected, as long as you're one of the 10. So since the order does not matter in which you're selected out of those 10 finalists, this is going to be a combination. So we have 51 contestants. This is a combination. We're choosing 10 finalists. So now if we use a calculator, we have 51 contestants. Math, probability, the third one down, this is a combination. We're choosing 10 finalists out of the 51 contestants. So there are 1.27 times 10 to the 10th different possibilities. So this is approximately 1.278 times 10 to the 10th. So if we write this out, 1278 followed by, we need 7 more zeros. So there would be approximately 12,780,000,000 different ways to select 10 finalists out of the 51 contestants. So that concludes lesson 9.1. Make sure you understand how to use the fundamental counting principle. Make sure you understand the formulas for permutations and combinations, and make sure you understand the difference between a permutation and combination. Remember, the main difference between the two is that in a combination, the order in which the objects are selected does not matter.